All right, so yeah, my name's Hernando. I'm a core developer at Parity. And today I want to give you an intro on ink, and then also go through one of the cool features of ink, which are called chain extensions. So the plan. First, I'm just going to give you an intro and give you an idea of why ink is important in the Dotsama ecosystem. Then I'll go through some code and actually walk you through writing this chain extension feature. For the first part, I'm going to assume pretty minimal background knowledge. But for the second part, I do expect you to know Rust, have worked with Substrate at the runtime level, and then have also written a smart contract. Actually, before I continue, I think I got to share my screen for the guys on here. So let me do that. All right, guys on the screen, can you see stuff? Yeah, cool.
Yeah.
All right, so a little bit about my background. So I started at Parity 3.5 years ago, actually working on the Parity Ethereum client. And since then, I've worked my way through a couple different projects, eventually landing on smart contracts. I don't work on the smart contract stuff alone, though. There is a big team behind me. So we've got, in the smart contract umbrella, we have 3 separate teams. So we have the team working on ink, the language itself. We have the team working on the contracts palette, which is really the operating system, the brains behind the smart contracts. And then we've got the team working on the UI and the tooling. So big shout out to them. All right, let's get to it. What is ink? So ink is a Rust-based embedded domain-specific language for writing WebAssembly smart contracts. And this is a mouthful. So I like to break it down into 2 main things. The first part is this Rust-based embedded domain-specific language. And really, you can think about it as ink is just Rust plus a little bit more. And one of our philosophies when developing ink is that we want it to be just Rust. This gives us access to all the nice features of Rust, like the strong type system, the mean yet helpful compiler, the giant ecosystem of crates, so third-party libraries, and then also the compiler support. This gives us a big advantage over something like Solidity, where you need to build all this custom tooling, you need to build your own debuggers and all this stuff. Whereas being within the Rust ecosystem, we get all this stuff for free. Now on to the second bit, this WebAssembly bit. So if you come from, so I guess maybe WebAssembly is this portable code format. And it's really nice for a couple of reasons. It's very lightweight, it's fast to execute, and we can generate deterministic code with it. And when running in a blockchain context, that last bit is super important. If you're coming from the Ethereum world, the analogy here would be Solidity in the Ethereum virtual machine, or the EVM. And WebAssembly has some advantages over the EVM. And just like we use Rust because it is general and it's supported by more people, so is WebAssembly. WebAssembly is an open standard, and it's supported by Google, Mozilla, Cloudflare, and a bunch of other companies. So we get a lot of hard work done for free as well. For instance, the LLVM compiler backend, we don't need to implement for WebAssembly. We can just let them focus on doing compiler stuff, and then we can focus on our core logic, which is writing smart contracts. If you're familiar with Rust at all, this won't look out of place. It's just a piece of Rust code. And you can go and run cargo check or cargo build, and it'll compile just fine. The magic of ink, though, is that in order to turn this Rust code into an ink contract, we only have to add these annotations. So let me just flip through that again. That's all we need to make this a valid ink contract. And behind the scenes, these little annotations are generating lots of code for you and making it WebAssembly compatible. And again, you can use all the Rust tooling, all your favorite things in order to do ink development. And that's really nice. So this conference is called Polkadot Decoded at the end of the day. So why are we talking about these ink contracts? So I'm going to talk you through 3 separate scenarios where we think ink really contributes to the Dotsama ecosystem. The first one is the most basic, and it's you can have a standalone smart contract parachain. This is a totally viable use case, right? We saw the success of Ethereum, and it's just a smart contract chain. Similarly, you can have just a smart contract parachain. I guess nowadays it's not good enough to be just that. There are teams coming out with unique value propositions like A-Star having, DApp staking, developer income, and that sort of thing. But at their foundation, they are smart contract parity. So that's one way to go. The second way is that you can actually leverage the power of Substrate to make more efficient dApps. So let's consider maybe a DeFi sort of parachain. You can provide a bunch of primitives, a bunch of hooks for really efficient, really common operations. So maybe like a token swap. And then you can let an ecosystem of developers build on top of these primitives. So yeah, because doing some of this stuff in the core smart contract logic is too slow and just doesn't make sense. So you can use a mix of this runtime development and smart contracts to really extend the functionality and the performance of your blockchain. Lastly, you can use smart contracts as your gateway drug into the Polkadot ecosystem. So again, if you've done runtime development, it's all Rust-based. If you want to build a parachain, that's also Rust-based. And then ink contracts are Rust-based. So you don't need to manage all these different languages throughout the stack. You can just learn Rust, get your developers up to speed on one development stack, one set of tooling, and work your way through. I guess on that point, what you can do is you can deploy your ink smart contract somewhere, see if you have a business use case for your application, if there's traction. When you see that there's traction, you want to invest more effort, you can start making a Substrate palette, really tune it for your use case, optimize it, and then if that's a success, then you can go and go full Monty into becoming a Dotsama parachain. All right, so for this next bit, I'm going to be walking you guys through some code. So the feature in particular I'm going to be walking you through are these things called chain extensions. And chain extensions are really cool because they allow you from ink to talk to the Substrate runtime in a native way. This is something you wouldn't be able to do with Solidity and the EVM palette, for instance. And I'm going to go through 3 different scenarios there, but I'll get through what these are later. So all the code can be found on here if you want to follow along. I'll give you guys a second to scan that. All right. So I've actually got the real QR code here. So. All right. All right, let's get to it. All right, so the if you actually did, so again, this is the real QR code if you did manage to get to it. The repo is based off, so let me show you. Is this text big enough for you guys? Do you want me to make it bigger? Maybe a little bigger. Good. So the repo is based off the contracts node template, which itself is based off the Substrate node template. And what it is, it gives you like very vanilla functionality on what a smart contracts chain should look like. So basically, it just includes a contracts palette. It includes a couple flags to enable unstable features and logging. And then it also uses manual seal for its consensus mechanism. So for development, that's really nice. It means blocks are only produced when things happen, and you're not just pumping blocks all the time. And then the couple main things, so we're going to be mainly working in this runtime and contracts folders. And then we also will be interacting with one of the palettes in this palette folder. Okay, so yeah, so in the repo, I went to contracts chain extension. And the first thing we want to do when defining a chain extension is actually define a trait. And we're going to annotate this trait with this chain extension proc macro. And that'll do a bunch of magic behind the scenes. We don't really need to get into it. When defining a chain extension, we need to provide the name of the method. And then we also need to provide an identifier. So this identifier is going to be used on the runtime side in order to figure out what function is actually being called. Because the runtime has no clue about what write to storage actually is. It'll just match on this extension ID. In a production sort of setting, you'd probably want some like, hex type thing here, like the message selectors. But for our purposes, just having a uint is fine. This first chain extension we're going to do is we're going to call into this template palette and just write a value to storage. I can show you the template palette real quick. So yeah, we're going to call this dispatchable. All it does is it takes some value, this something, and then writes it to storage. So we want to be able to call that from inc. So we define our method, and then we need a message wrapper. So in our actual inc contract, in the message, we can actually, before we get to that, there's one more thing I got to tell you guys about. So whenever we work with contracts, we have this concept of an environment. An environment is a sort of like the execution context for the contract. And when working with Substrate, you know that everything is generic and extensible and all this stuff. So we can't make any assumptions as to what environment the smart contract is going to run in. We don't know what the actual block number is going to be. We don't know what the real account ID type is going to be, all that sort of stuff. So we need to give contract authors a way to customize that. And we do that through the environment. Out of the box, we do have a default environment because most Substrate chains have similar assumptions. But again, we need to be able to give contract authors a way to modify that. And one of the things that makes up this environment is whether or not we have chain extensions. So we need to implement this environment trait for our custom environment. We can leave everything else the same, so we can just go through the default environment, but then we need to tell it to use this chain extension. And this chain extension is what we've defined here. Okay, and then we also need to tell the inc contract to use our custom environment, so that's what this line will do. All right, now we can go back here. So notice how we're accessing our chain extension through the environment because it's part of it. And then we can easily just call like a normal REST function right to storage. And that will, behind the scenes, tell the contracts palette to dispatch it. All right, the next thing we'll do is we'll actually check how the chain extension is implemented. So in the runtime, we need to define a module where we'll have all our chain extension code. And really the only thing we need to do is implement this chain extension trait. So this chain extension trait comes from the contracts palette. Let me move this. So palette contracts provides this chain extension trait. And all we need to do is implement this call function. This enabled function will be implemented by default for us, so we don't need to worry about it. And the call function, all it does is it takes these function IDs that we've defined and the environment. And then from there, we'll be able to know how to correctly dispatch logic. So our implementation of this chain extension trait needs to access certain palettes. So we're going to be accessing the contracts palette, the template palette, and later on the scheduler palette. So we need to have those trait bounds in there. This I'm not going to talk about just yet. Yeah, and then we can actually go into the implementation block. So the first thing we need to do when writing a chain extension, in contracts and chain extensions communicate through the shared memory buffer. And we can access this memory buffer in a couple different ways. We can access it in a read-only mode and a write-only mode. We actually want to do both read and write. So we can use this buff in, buff out to indicate that this is how we want to read it. After that, we're going to match on the function ID which got passed into the chain extension. So remember that the chain or the function ID that we defined for this first one was 1. So we can just match on 1 and then have our implementation logic with it. One nice thing about Rust is that it makes you be explicit. So actually, if we don't match on anything, we'll just panic and throw our hands up. But you need to handle that case. Next thing is we do have a function argument here, right? So we have the value that we want to write to storage. We need to somehow read this out of the memory buffer. And the memory buffer gives us this nice function called read as. And what it'll do is it'll try and, from the memory buffer, decode the type, or the bytes into the type you specify here. And if it doesn't, it'll just bail out with an error. The nice thing about this is that you as a chain extension author don't really have to think much. You can just give it a type. But in order to do this, the type needs to be a static type, which means the size and needs to be known ahead of time. If you're using something that's dynamically sized, you need to go through a different sort of mechanism, and we'll get to that after. Since we've moved from writing contract code into writing runtime code, the paradigm for how we do resource metering changes. So when we're writing contracts, we're in a gas metered world. And we do this because we assume that every smart contract running on our blockchain is malicious. It's going to try and use all our resources without paying for them. So we need to give them a hard cutoff for their computation. Runtime code, on the other hand, is trusted. We assume that it'll execute correctly and faithfully, and that it'll only use the resources that it's supposed to. That means as a runtime author, you need to keep track of all your weight. So whenever we write a chain extension, we also need to keep track of how much weight is being consumed. So if we go back to the palette, you can see that it's got a weight annotation. So we're just going to steal that and use that as the weight that we're going to charge whoever calls this chain extension. Ideally, what you should be doing in a production environment is benchmarking your palette using Substrate's benchmarking framework, and then going through the weight info struct and getting like the real benchmark weight value from there. However, I was too lazy to benchmark the template palette, so I'm just going to hard code it. But it's really important to charge the weight. Otherwise, you open your chain up to DDoS attacks. Next thing we're going to do is actually we're going to craft a call to call this palette. So again, we know that the do something dispatchable takes some origin, so the caller of the call, and then some value that we're going to write. So we're going to give it the caller that called the smart contract. We're going to just forward that through, and then we're going to forward through the value we got as well. And that should be it. Using this, we should be able to write using the template palette. So next thing we need to do is we actually need to compile our contract. So we'll do that. And then we also need to run our node. So maybe a little tip for you guys as well. If when you're doing development, you don't need to build the WASM runtime. You can get away with just building the native runtime. So it saves you a bit of time. In our case, we also want to build with this locked flag. So if you've worked with Substrate at all, you know there's no formal releases. Everything's just pinned to GitHub dependencies. And Cargo is very eager when you're pulling some of these dependencies in. And often they're breaking changes. I don't want my demo to break in front of you guys, so I'm just going to stick to whatever's in the lock file. So again, also a good tip for development. See our contract built OK, and then we can run this chain in development mode. I'll give that a second to start up. And then if you guys have any questions at this point, just like raise your hand and yell at me. I don't mind. Interesting node name. Fish snow. All right, so I'm going to be using the Polkadot.js apps for this. Typically, like for contract development, I would be using our like contracts UI. But because we're doing a little bit of runtime development here, this is just more convenient. So first thing I'm going to do actually is just go to this to the chain state and check what the state of the palette is. So you can see that the template palette has nothing stored. And this is expected. We haven't done anything yet. Let me just duplicate this. Next, we're going to go to the contracts tab and actually upload our contract. OK, cool. That got deployed. And then we're going to call the write to storage message. We can just write one, whatever. Sign that. We can see that an event got emitted. The template palette stored something. And then we can double check here, and we can see that the storage was indeed updated. So we were able to call into the runtime from an in contract. So that's pretty cool. But we're not done there. We've got a lot more to go. So the second thing I want to show you guys is how to use a custom type and how to handle errors. So one nice thing about Rust programming, the error handling is actually pretty decent, and we want to be able to take advantage of that. So let me start by showing you, I guess, the custom type we're going to be using. So it's just a simple wrapper around a vec. And I'm doing this because we can't know the size of this ahead of time. So we need to handle it differently in the chain extension. Something we need to define for our type is actually, we need to be able to encode it and decode it. Again, this goes back to that memory buffer. We need to be able to read these somewhat like seemingly random bytes from there. So we need to implement this. As far as the error handling goes, we need to define our own error. And so I've defined this extension error. And there's two failure modes here. So the first one is if our chain extension fails somehow. And then the second one, if we fail to encode or decode something from storage. We do need to implement two more traits for our error. One just makes it a lot more ergonomic to handle errors from the chain extension. And that's this from status code trait. When the chain extension fails, and actually I can show you, or even when it, chain extension, yeah. So I can show you, when the chain extension succeeds, for instance, we return this ret_val thing. But ultimately, it's just a wrapper around a uint. So that's the only way the chain extension communicates. And we need to be able to translate this uint into a real Rust error that we can handle on the ink side of things. So that's all this trait kind of needs from you. And then we also need to just make sure that if there's an encoding error from the scale codec, that we can handle that as well. The message I've made is pretty silly. We're basically going to tell it whether or not we want it to succeed. And I do that as well. Like, so here I have two different sized vecs depending on how you call the message. Again, just so we can see the case where we dynamically handle a custom size type. We'll call the chain extension the same way as before, but now we can actually handle this error using the question mark operator. When you're writing in contracts, if your messages return a result and it's called from another contract, you can handle this gracefully. Things don't necessarily need to revert. If a user calls a result and it fails, then things do revert. So the behavior there is slightly different depending on the context. But it's nice. We give you the option to handle it if you need to. So in the implementation, instead of using the read as function as we used before, we have to use this read as unbounded because we don't know ahead of time how many bytes we're going to have to read. Luckily for us, the environment also gives us this in length, so it knows how many bytes it received. So we're just going to read that many number of bytes and decode it into our custom type. I did have to make a wrapper type, or I guess maybe like a copy type around our ink type in order to decode this correctly. I think ideally what you should do is you should probably define your types in some module or crate and import them across both your ink contract and your runtime or in your chain extension. But again, just to make this quick, I just copied the type here. The type definition is pretty easy. But we need to know what to decode this buffer into, so that's why we had to do that. As before, we need to charge some weight. And then our logic here is going to be that if the size of the vector, if the length is a power of 2, then we're good. If not, we're going to return an error. And again, the chain extension only communicates with these uint values. So we need to handle that on the ink side. And then in order to just kind of show that it can still talk to the runtime, I'm just going to store the length here. So nothing too crazy. All right, let's go. What's a custom type with result? Oh, too big. So first, let's run this with the success is no attribute. give that a go, and we can see that it failed. So our contract reverted, and this is exactly what we'd expect when from this line, because it'll try and it'll bubble up the error, and then because we're a user calling the contract, there's no way we as a user can handle it, so it just bails out. If we now run it with the success is true flag, we can see that it got included in the block. And if we check over here, we can see that the length of the vector got stored in storage. So everything's working as intended. Are there any questions here? No? All right, so then for my final trick, I'll be showing you guys how to do a round trip from inc to the runtime and back to inc. So I made a handy little diagram here about what we're going to be doing. So we're going to be calling an inc message. In the runtime, we're going to build a call to the contracts palette. Then what we're going to do is we're going to build a call to the scheduler palette. And in case you're not familiar with the scheduler palette, it is something where you can tell it, hey, I want this action done at a future point in time. And when that, and typically it's a block number. And when that block number is hit, it'll execute automatically. So that's really convenient. So we're going to schedule a call to the contracts palette at some future point. When that call is triggered, that call will call back into our inc contract and emit an event. I guess to also give you guys maybe a different sort of visual, I'm a big fan of ASCII art if you can't tell. Yeah, so the inc contract's going to call into the chain extension. That's going to build this kind of like nested call, and then that's going to talk to the inc contract. So again, the definition here is pretty easy. We're just going to ask for a block number when this thing wants to, or when this thing should be triggered. And then we're, again, going to handle the error case. Oops. So the message itself is pretty simple. Again, we're just going to wrap the chain extension call. And then the handler, all we're going to do is emit an event. One thing to note here is that each message has a selector, so an identifier, and we're going to manually hard code the selector here just because we want to know from the chain extension what this is going to be. If maybe you don't have the luxury of handcrafting this, you can check from the metadata. So we can do this. Schedule. Yeah, so you can see that the metadata. So the metadata describes the contract in a non-code related way. So if you wanted, like, how does the UI know that we have 4 functions? It goes through the metadata. Because on chain, this is all just a wasm blob. It's like you can't read this. So the metadata is that translation layer. And as part of it, we have the message selectors. So you can see that actually for our call, you can see it's the 0x0 coffee selector. But usually they're more random than that. Cool. Let's go to the implementation of our chain extension now. So again, we can, because it's just a U32 argument, we can just read it using read as. This time we actually do have access to the benchmark weights of the scheduler palette, so we can use that to charge weight. And I guess how I found this is I just went to the code of the scheduler palette and took that weight directly off there. Since we're building a call for the contracts palette, we do need to get some extra information out of our execution environment. So we don't only need the caller, but we need the address of the smart contract that we want to call into. We need any value that was transferred alongside the smart contract. And then we're also going to set the gas limit. So what we're doing here, we're just going to forward all the remaining gas without left. We also will need to encode any message arguments. So we need to tell it, hey, what function do we want to call? So we encode this selector into some data blob. And then we also have this magic number that's part of the event, so the second argument. And we're going to encode that as well. we need to build a call to the contracts palette, and we need to make a distinction between two types of calls that we have in Substrate. We have runtime calls, which indicate what palettes that make up your runtime are callable. And then, so that's what this outer call is. And then this inner call is a palette call. And this says, this palette, which has calls, has these certain dispatchables. So there is a distinction between both of them. The scheduler palette expects one of these runtime calls, not one of the palette calls, which is why we need to wrap everything. We also do need to add a little a trait bound here in order to say that we can do this conversion properly. And then we can go, just like we wrote to the template palette, we can go ahead and craft our call to the scheduler palette. Again, passing in our contracts call as an argument. All right, let's go see how this works. So we can schedule a call at block, let's say block 6. I do need to use a little bit higher block weight here. So I found that 5% is working for me. And send that. We can see that the scheduler palette emitted an event that something is going to happen at block 6. We can just run some other things. So again, we're running manual seal, so nothing gets updated until we do an action. So I'm just going to run something. Now we're on block 6, and you can see that the scheduler successfully dispatched something, and then our custom event was emitted. So we were able to call back into the inc contract at a later point in time. So I think that's pretty neat. Just another note on this: you don't have to go through the scheduler palette. You can actually take this inner call, and in your runtime here, or in your palette, just plop it somewhere, and then call this extrinsic and call back into an inc contract. So it's a totally legit way as well. All right, so I think that's all the code I've got for you. Let me just see what else is on the presentation. Yeah, so that's all the code I have for you. Are there any questions for the for the workflow on that last thing? No? All right, so if not, then I guess the final thing, if maybe you weren't able to follow along, this is your first time learning about inc and contracts, a couple places for you to get started would be the actual inc repo itself. Really, that's the gateway to everything. We also do have some tutorials on the Substrate website that get you from 0 to deploying your inc contract. We also do have our own kind of internal, or not internal, but more inc-specific documentation portal at inc.substrate.io. So it's a good learning resource as well. We have an element chat where we post announcements and that sort of thing. And then we also have a Stack Exchange. So if you've got any questions, if you're running into issues while going through the tutorials or building your own contracts, drop us a question on the Stack Exchange. There's a lot of people, not only from the Parity team, but from the community answering questions there. All right, so with that, I'm done my presentation. Again, if you've got any questions, just find me or yell at me now. So yeah, thank you.